What is this live stream? This is a YouTube thing, or is it?
Yeah, this is a YouTube.
Okay.
Yeah, so shall we start now?
Yeah.
Sure.
Yeah. Okay. Yeah, welcome everyone for today's talk. Today, we're fortunate to have Anton Dochtermann from Texas State University, and he will be talking on Shellings, chordality, and sentence conjecture. Yeah, over to you.
Okay. Yeah. Thanks, Anurag. So thanks to the organizers for the introduction and the invitation. As I mentioned, I've never been to India, so this is my first time. Although this doesn't count, I guess. So still would like to visit at some point. I want to talk about so these ideas here: Schelling, chordality, and Simon's conjecture. I'm not entirely clear what the audience is here, so if you have questions, want me to clarify anything, let me know. I should say that a lot of this is joint work with, a few people. So Culbertson, Goralnik, Stiller, and then another project. So I'm going to sort of summarize a couple of different projects here, kind of in the umbrella of these notions. So let's see, let's start off from the beginning. So let's let delta be a simplicial complex, which I do assume people have seen before. So let's say a simplicial complex on vertex set. So I'll usually, think of the vertex set as just 1 through n. So it's always going to be a finite thing, and we'll just specify it to be 1 through n. So as you know, a simplicial complex is combinatorially, it's just a collection of subsets of, say, 1 through n that are closed under taking subsets. And delta is said to be shellable if there exists an ordering of its facets. So say F1 through Fk. So the facets are the inclusion-wise maximal faces, right? So maybe I can draw a little simplicial complex over here. So if this was, actually, so I'm going to be dealing with pure complexes. So let's just draw this. So that the facets here are going to be 1, 2, 3, 2, 4, 5. Of course, I can draw a simplicial complex as this geometric object. The facets are the maximal, under inclusion, the maximal collections here. And we're going to say it's shellable if there exists an ordering of its facets, so that whenever I take Fi and I intersect with what I have so far, so j less than I, so this should happen for all I, that if I take Fi and I intersect with the simplicial complex I have so far, then this is pure of codimension 1. So a couple things I should have added here. So I'm going to be thinking about a pure simplicial complex. I should say that the notion of shellable actually works for more general simplicial complexes, but let's just let's assume that delta is pure here. It's going to make our life easier. Okay, so what's the idea behind shelling is that it's kind of mimicking what you would do when you say peel an orange, right? So it's kind of the reverse process of peeling an orange. So if you start with something like this, 1, 2, 3, then I can add this next face 3, 4, 1, 3, 4, because it intersects the previous thing with, so if I started at 1, 2, 3, that would be my first facet. I add 1, 3, 4. 1, 3, 4 intersects 1, 2, 3 in this codimension 1 face. And then I could say, add in 2, 3, 4. 2, 3, 4 intersects in this, right, codimension 1 simplicial complex there. Okay, so that would be a shellable simplicial complex, this thing here. Note actually that this is not shellable. There's only 2 facets here, and there's no way I can glue one. I can't glue one facet to the other along a codimension 1 face. Another kind of not shellable example would be something like, if you had, I don't know, something like this. Let me try to draw this. So if you had some sort of triangulation of something like this, well, yeah. So this is a bunch of triangles glued together, and if they connect at a single point here, that's not going to be a Shellable simplicial complex. There's no way to order the facets of that thing so that the intersection with the previous complex is codimension 1. Okay, so again, I'm not sure who's seen this, who's not seen this. That's kind of the, and that is the definition. I was going to say, slow me down if you haven't seen this, but
what is a pure?
Yeah.
What is a
okay,
pure?
sorry. Yeah. So okay, good. So a pure where delta is pure if all the maximal, all facets have the same cardinality. Yeah, where a facet is a maximal element of, under inclusion. So, that thing I just drew is pure. This is pure. Something that's not pure would be, if you had 1, 2, 3, and then you had something like this. So here 2, 4 is a maximal face, but it's not the same size as 1, 2, 3. The facets here are 1, 2, 3, and 2, 4. Okay.
So a pure is a term for a simplicial complex, right? So, but when you said
Yeah.
fi intersection union of that quantity fi, where j is from 1 to I minus 1, that is a set. That is a set in the simplicial complex.
Yeah. So I'm being a little bit lazy here. So I'm going to take the simplicial complex induced by these things.
Okay.
Yeah. So yeah, I'm being a little bit lazy, but yeah. So you're right. This is a collection of facets. So I'm going to take the simplicial complex, maybe induced by these things. Some people put the, sorry,
Okay.
Can't see that. Yeah, I'm trying to, hide some of the details here, but yeah, as you said, that's totally right. That, what I wrote there is actually a little bit of a lie, but if you think about the simplicial complex induced by these sets, so take all the subsets, right? That's right. So take all the subsets you see by these, by these things, and you get a simplicial complex.
Yep.
Okay, so who cares about Shellings? So I'll say the existence of a Schelling implies, well, strong conditions, I'll say, on delta. So for instance, the topology, it turns out that if you're Shellable, then delta will be is homotopy equivalent to a wedge of spheres. And I should have said, so if my complex is pure of d-dimensional, then it will be a wedge of d-dimensional spheres. It also has some nice consequences for the algebra, the underlying algebra here. So that it turns out that if you're Shellable, then the Stanley-Reisner ring, well, let's say K delta, is what's called Cohen-Macaulay. So, I mean, you can think of that as an algebraic condition. In fact, it is topological as well. But we think about it in this algebraic context. It turns out, I'm not going to get into this too much at all today, but this is one reason that people care about it. If you've seen Stanley-Reisner rings before, and then some combinatorics comes out of this. This provides, so if you have a Schelling and you can keep track of how these things intersect. So again, a Schelling is just an ordering of the facets. And at every step, I take the intersection of, well, the complex induced by that facet intersects what's there so far. And if you look at kind of the structure of those intersections, this provides a way to compute the H vector. Okay. So again, H vector is maybe something you've seen. It's a translation of the F vector, important combinatorial invariant of the simplicial complex delta. Okay, what else do I want to say? So okay, so that's nice that Shellings have nice applications, and it also is true that Shellable complexes kind of arise in nature. So okay, so what do I mean by that? Well, examples include well, I guess the way I said this here, examples include the boundary complex of a simplicial polytope, right? So as you probably know, a polytope, right, is the convex hull of finitely many points in Euclidean space. And if it so happens that the boundary of that polytope is a simplicial complex, then it's a shellable simplicial complex. I should say that there's notions of shelling for more general polyhedral complexes. So actually all polytopes are shellable via what's called a line shelling. Other examples include independence complexes of matroids. I had more things that I wanted to list here, but I think I'm running out of room. So there's various complexes you get from Coxeter groups that are shellable. So it turns out that shellable complexes are, they're out there, and they're that's kind of why this was invented, I would say. On the other hand, so more recently, so shellable complexes kind of arise in nature, but they're at the same time it's hard to tell if something's shellable. So more recently, it was proved that, well, determining shellability is NP complete. So if you give me a complex, say on n vertices, and I ask you, is that shellable, then that's an NP complete. Of course, it's in NP because you can check that your given shelling is actually a shelling, but to determine if it's shelling, it's NP hard. And this is due to, well, I'm going to write out the first name and say et al. Here. So there's 5 or 6 authors on this paper. But that's a recent paper from just a few years ago. I think the consensus was that this was true, but these folks actually proved it. So I'm going to sort of use that as inspiration to say, well, okay, so if you give me a complex, it's not going to be easy to tell if it's shellable. But what about, when does a greedy algorithm work? So, and so this is going to be a definition now. A shellable, and again, pure simplicial complex delta is said to be extendably shellable if any shelling of a subcomplex can be extended to a shelling of delta. Okay, so what do I mean a subcomplex here? I mean, so what I mean by this is so again, I'm being a little bit lazy here, but subcomplex, I mean a simplicial complex that's generated by a subset of the facets. Okay, so the idea here, of course, is that I have a simplicial complex and I want to know if it's shellable. So I'll just kind of if I go back to the definition here, I'll just try.
So I have a small question, Anton.
Yeah.
So
sure.
when you say that any shelling of a subcomplex can be extended, so I assume that whenever you say some simplicial complex is shellable, there can be more than one shelling orders, right?
Oh yeah, that's right. So this is saying that there's lots of them somehow. I mean, so that's a good question. The sort of the number of shelling orders. Actually, I'll get that. That's a good question. And let me actually.
And then this will be applicable for. So this means that if you take any subcomplex of the facets, for each of these subcomplexes, one should be able to extend it to the full shelling of the.
Well, not any
complex.
subcomplex. No, so be careful. Not any subcomplex. Any shellable subcomplex, right? So I need to be able to shell that subcomplex.
Okay, so you look at all those subcomplexes of delta which are shellable, and then any of the shellings of these shellable subcomplexes should be extendable to a shelling of delta.
Mm-hmm.
Okay, so that is when one would call it extendably shellable.
Yeah, I mean, like I said, the idea I'm trying to get across here is that I can just start, gluing on facets that satisfy this intersection condition, and I'll never, assuming that it's a shellable complex, I'll never get stuck. So this is just trying to say that, a greedy algorithm works, that if you gave me a shellable complex, then I just start shelling and I'll never get stuck because, you're assuming that I can always keep going.
Okay.
Okay.
Yeah, thanks.
Okay, great. So, and actually that reminds me that, this question of kind of what are the good shelling orders, that's a nice question that comes up in the background here. I mean, I'm tempted to kind of to take a left turn here, but if you've seen the notion of a matroid, which I'm hoping to mention later, the independence complex of a matroid has this really nice, in fact, characterization that says that any lexicographical ordering of the facets is a Shelling. Meaning, if I order the ground set any way, then I can then list the facets in lexicographical order, and that will always be a Shelling. So that's kind of a nice, that's in the spirit of this kind of what are the Shelling orders. This is kind of I think kind of an amazing fact that actually characterizes a matroid. Okay, so extendably shellable complexes don't seem to be around so much. So let's say I wrote down a couple of examples. So what is known to be extendably shellable? So facts, what's known to be shellable is that any two-dimensional triangulated sphere is, let me call this ES. So maybe I should have ES for extendably shellable, so I don't have to write that every time. Any two-dimensional triangulated sphere, which is necessarily polytopal, is extendably shellable. What else? So if you, Kleinschmidt also showed that any d-dimensional sphere on d plus 3 vertices is extendably shellable. And there's not too many other kind of known classes. On the other hand, so non-examples exist. Ziegler has shown that there exist simplicial for polytopes. So polytopes are necessarily shellable, but these are that are not extendably shellable. So I should probably attribute all of these, but I know that this one is Ziegler. That took some work to prove. So the conjecture that I want to kind of focus on here, so as in the title of the talk, well, let me just recall a little notation. Let me call it this. So delta n minus 1k is the k skeleton of the simplex on vertex set, well, n, which was 1 through n, right? So the k skeleton of a simplex is all k subsets of 1 through n. So for instance, if k is 1, this is just the complete graph, and you've got the boundary of a tetrahedron, I guess, is delta 2, 3, and so these are the k skeleton of a simplex. And Simon's conjecture says that that these guys are all extendably shellable. For all k, n, and n. Okay. So and I should say that the k skeleton of a simplex is shellable. In fact, any skeleton of a shellable complex is shellable. And of course, the simplex itself is shellable because it's just a single facet. And it's a fact that if you take the skeleton of a shellable complex, it's also shellable. And so, this is, again, kind of motivating some of our work here. So this is trivial, I should say, for k equals 0 and 1. And it was proved, I think a few years ago now by, Bjorner and Eriksson proved that k equals 2 case. In fact, what they show is that any rank 3 matroid is extendably shellable. So if you know what a matroid is, they actually prove the stronger statement. about rank 3 matroids. And one example of a matroid is what's called the uniform matroid, is exactly the K skeleton of a simplex. So if you take all actually, I got to be a little bit careful. Right? These are K+1 subsets because I'm taking the, of course, the dimension. There's this usual shift in dimension, right? So if I want to look at the, say, the 0 skeleton, then I'm looking at cardinality 1 things, right? Question?
Yeah, Anton, I have a question. Like, why we are interested in the extendable Shellability complex? I mean, what are the extra benefits we have here?
I didn't quite hear.
I mean, why we are interested in the concept of this extendable Shellability? What is the extra benefits we have?
Yeah, I mean, I tried to motivate it. I mean, I think it's a natural question for me that, if I have this property that's defined by this recursive thing, that, how do I know when a kind of greedy algorithm works? I would say that this fits into a larger context of, these kind of conditions on a simplicial complex, or, any sort of, I mean, folks who might be working in some combinatorial topology, you might be more familiar with the notion of like collapsibility and, the difference between collapsibility and, say, simple homotopy equivalence, where, it's often the case that you define this property in terms of like the existence of a sequence of things. And it's often, the case you want to know, can I do it greedily? I don't know. For me, it's a natural thing. I don't know if I can say more than that. Does that answer your question? So you have these notions of, there exists this sequence of things. When can I kind of just, only apply, say, collapsings instead of these expansions or something like that? I don't know. So that, for me, it's it's a natural thing to ask. Okay. So I want to talk a little bit about kind of what we did with this. So it turns out that, here's another reason. For me, I think that extendably shellable kind of connects to these other areas of mathematics. So that's another reason that I like to study it. So it turns out, for instance, that there's a connection. So the next kind of section here is going to be connection to chordal graphs. So changing gears a little bit. So recall that a graph G, so just, the world of graphs, so we'll take simple graphs, no loops, no multiple edges. A graph is chordal if there does not exist, let's say, any induced cycles of length bigger than or equal to 4. So in other words, any cycle of length 4 or more has a chord. So I don't know, like something like this, so this is, now I'm drawing a graph. So that's chordal. Something that's not chordal would be something like this, right? Where you have, that's not chordal because you've got this induced 4 cycle, right? So you're missing a chord in there. That's why it's not chordal. Okay, so chordal graphs are, a huge industry. People love them. There's books written about chordal graphs. And, a couple of years ago now, Culbertson, Guralnik, and Stiller, they gave a new characterization for chordal graphs. They said that a graph G is chordal if and only if G can be obtained from the complete graph Kn. So this is the complete graph. This is the graph on n vertices with all possible edges, from a sequence of removing what are called exposed edges. Okay, so what's an exposed edge? Where an edge E is exposed if it's contained in a unique maximal clique. So let me show you an example of this. Let's see, did I have an example I wanted to use here? So you know, I think I'll come back to this example later. So here's the complete graph on 5 vertices. So let's say 1, 2, 3, 4, 5. Now, okay, so let me let you guys digest this. So this is a characterization of Chordal. I'm going to show you an example of how you obtain a graph from Kn from a sequence of removing exposed edges. Okay, so I start with Kn, which is the graph on all, you know, with all the edges possible. And exposed edges means that I'm in a unique maximal clique. So a clique, if you haven't seen that before, that's a subgraph that's also complete. So this is a complete subgraph. And to be a maximal clique means it's a maximal complete subgraph. So if you start with K5, of course, the maximal clique is just itself. So any edge is exposed. We'll take out 1, 2 here. See if I can do this. Right, and now I want to keep going. So I want to now take out, let's take out 1, 3. So notice that 1, 3 is in the clique 1, 3, 4, 5. And it's, you know, when I say it's a unique maximal clique, it's not in any other maximal clique. So I'm going to take out 1, 3 now. See if I can do this. So this is here, here, here. Do I have everything now? Okay, so I've taken out here 1, 2, and here I've taken out 1, 3. Now, I mean, just to give you a non-example, notice that 4, 5 would not be allowed now. 4, 5 is not, you know, it's in 2 maximal cliques. 4, 5 is in the clique 1, 4, 5, and also in the clique 2, 3, 4, 5, right? So 4, 5 would not be allowed. I want to do one more that I'm going to use later. I'm going to take out 1, 4, and that would leave me with something like this, right? So 1, 4 is exposed. Okay. Okay, so that's what I mean by removing maximal, removing these exposed edges. And so this is a combinatorial argument, and kind of surprising maybe that it's new. I mean, so chordal graphs have been around for a long time. But so let's see.
Just a small question. So in particular, one can always get rid of hanging edges.
That's right. So hanging. Okay, good point. So I'll come back to this in a second, hopefully. But that's right. So if you have an edge that is its own clique, right? We call those like facet edges. That's right. So if an edge is its own clique, so 1, 5 you could remove right now because it's its own maximal clique, right? So that's a good observation. Let me come back to that in a second. So one thing we can prove here, so this is kind of one example. I mean, it's a special case of something we can prove, is that. So how does this tie back into Shellings and things like that? So it turns out that, suppose G is a graph on vertex set 1 through n, then a sequence, let's say E1, E2 through, I don't know, EK, is, a sequence of removing exposed edges. If and only if, let me write it as F1, F2 through Fk is a Schelling sequence. And what do I mean by F1 through Fk, where Fi is just the complement of EI. So the complement of EI in the set N. So I guess I could have written this as N, backslash EI. Okay, so let me, so what I'm saying here is that if you start with a graph on vertex set 1 through n, say, then when I remove sequence, remove these edges, so these are cardinality 2 subsets of 1 through n, like I did here. So let me just show you this with this example here. So when I remove 1, 2 from the edge, that corresponds to the complement of 1, 2 means I start with 3, 4, 5, right? So right, so this removing 1, 2 means I start with 3, 4, 5. And then I remove 1, 3, which means I glue in 2, 4, 5. All right, so that's what this picture is, removing 1, 3. And then removing 1, 4 means I glue in 2, 3, 5, right? So this, and so you see that this is a Schelling, and that's, it's not too hard to see that this is, an if and only if statement, that I have a Schelling if and only if this is a sequence of exposed edges. Now, one thing that we can, so again, this is actually a special case of a more general theorem that I'll hopefully mention in a second, but one corollary of this, which is pretty nice, I think, is that, basically what you've now done is you've reduced the case of, Shellings of a certain complex to the case of exposed edges in chordal graphs. So, what we now can do is we can use all this theory of chordal graphs. So if you've seen chordal graphs before, you know that there's various characterizations. There's notions of simplicial vertices, right? So maybe I'll say this: we can use kind of technology from chordal graphs. Chordal graphs.
Anton, I have just a question.
Yeah.
Okay, so when we are saying this F1, F2, Fk is Schelling sequence. So what are the simplicial complex you are taking? Then you are saying that F1, F2, Fk is Schelling sequence.
That's right. So I started with 5. So I'm thinking of this as a simplicial complex on 1 through 5, where some of my vertices are not being used as vertices, right? There's a ground set, and then there's some elements of the ground set that are not being used. So, again, I'm abusing some notation here, but the simplicial complex is induced by these facets. Does that make sense? So as usual, I'm going to describe a simplicial complex by just its facets, right? I can do that because it's closed. Okay. Okay. So here's. Is that okay?
Yeah, it's fine.
Okay. So here's what we can prove: is suppose now delta is a d-dimensional complex on, let's say, d plus 3. Well, on at most d plus 3 vertices. Then delta is actually shellable if and only if it's extendably shellable. Okay, so that's actually, this is generalizing some of those statements that maybe I can't find right now that were in previous slides that that said that if basically what you're saying is if you don't have too many vertices, then shellable and extendably shellable are equivalent. And this is actually tight, I should say, since there exists, in fact, 2-dimensional complexes on, let me get this right, on 6 vertices that are shellable but not extendably shellable. So, okay, so let me just say, this theorem that we had about this one that I had here, this theorem about, having graphs, removing edges being exposed if and only if you have a Schelling sequence. We have a generalization of this for a higher dimension. So we can also generalize this. So I should say that, we can now let C be a clutter, a D clutter. So this is just a collection of D subsets of N. And, so if you have a collection of, say, 3 subsets of 1 through 5, right, you can still talk about the notion of, and so let me call these edges still. So this is just like a hypergraph. I mean, it's the same word as a hypergraph. For some reason, people call it clutters in this context. So you can still talk about the notion of exposed. You can talk about the notion of cliques and exposed edges. So I'll just say notions of cliques and exposed edges are defined as above. So, what is a clique? It's a collection of vertices of the underlying clutter where every D subset is actually an edge of your clutter. And an exposed edge would be an edge where you're uniquely, you're contained in a unique maximal clique. Okay, so you can show as above. Well, I'll just say, I think in the interest of time, I'll just say I'll say the same statement above holds. So I've decided to just do the sort of case that you're taking a graph. But what I'm trying to say here is that if you just replace this with hypergraph, I went through the graph case just I think that's more familiar to everyone. If you replace this with hypergraph, then you get the same statement. Okay. Now what's happening is that you don't have just cardinality 2 subsets, right? So therefore, these things will now be arbitrarily sized facets. Okay. But the same theorem holds, and I should say that the way we prove this, is to go through some commutative algebra. So the proof goes through some concepts in commutative algebra. So just some buzzwords, what are called linear quotients of monomial ideals. Etc. I should say that this corollary, of course, breaks down now. It's not going to be true that shellable and extendably shellable are the same, but what this does lead to. So this leads us to some notions of higher dimensional chordality. This leads us to a notion of higher dimensional chordality. So you can say, a D hypergraph or a D clutter, let's say C, we'll say is chordal if and only if it can be obtained from this complete clutter. So K and D, this is the complete D clutter, complete D hypergraph. By a sequence of removing exposed edges. And I think that's kind of the idea here. And this leads to some. I think I'll have to skip some of the sort of particular applications to Simon's conjecture, but this leads to a rephrasing. So in particular, a rephrasing of Simon's conjecture. And also applications to, let me just mention this, a generalization of Froberg's theorem. So Froberg's theorem is, if you haven't seen this before, this is an algebraic characterization of chordal graphs. So Froberg's theorem says that a graph G is chordal if and only if the quadratic monomial ideal generated by the non-edges is has a linear resolution. Okay, so I know this is not a commutative algebra kind of seminar, so I think I'm going to leave it there. Let me just say, I'm kind of running low on time here. So, kind of from here on, this has now inspired some research on my end, at least, that says kind of, so what I want to now kind of study is, how complexes can get stuck So, kind of the last section here is how complexes can get stuck in the process of shelling. So, again, Simon's conjecture says that if you start shelling something, you'll always be able to finish it off to the K-skeleton of a simplex. And so, one thing you can ask is kind of what does a stuck complex look like? So if you start shelling and you can no longer shell, you can use some of this technology that I haven't quite spelled out, but you can actually understand some topological properties. So I'll just say kind of understand topological properties. So I should say actually that if I go back to this example, so just to maybe kind of whet your appetite or intrigue you a little bit here, if you notice, for those of you who work with clique complexes, if you look at this clique complex, of course, this is just a simplex. Every time you remove an exposed edge, you are preserving its simple homotopy type, right? Except when, Shuchita pointed out, if you remove one of these clique edges, so as long as you're not removing one of those, themselves maximal cliques, the edges that themselves are maximal cliques, you're preserving the simple homotopy type. So this process of removing exposed edges is preserving that homotopy type. And so if you've kind of reached a place where you're stuck, you know that you have a certain topological type that then has to also, not allow another exposed edge. And so this has some applications to, e.g. via simple homotopy. And then the last thing I want to say is that we kind of noticed that when we were studying this question, so when you start with a complex and you start shelling, we noticed that if in the process of shelling, so let me just kind of motivate this with a little kind of cartoon here. So maybe I'll just say kind of weakenings of Simon's. That's the last kind of topic that I want to talk about. So again, Simon's conjecture says that I start with any shellable complex, I can finish it off. So let me actually do this with a definition. So a simplicial complex, delta, let's say, is shelling completable if if any shelling of delta can be extended or completed, to a shelling of this skeleton, right? So this is on vertex set N as usual. Okay. So you guys see the difference. So we couldn't call it shelling extendable because that was already taken. But notice that Simon's conjecture says that all shellable complexes are shelling completable. So let's call this SC. Okay. So what I'm trying to get at here is that in the course of studying Simon's conjecture, we notice that if you start shelling something, let's say I start shelling something with some sequence, I don't know, up to Fi, we notice that if this thing has a particular structure, for instance, if it's a matroid, if you're familiar with that, we notice that you could always finish it off. We could always finish the shelling off to this full K skeleton. Okay, and so it's of interest now to say which class of simplicial complexes are shelling completable. And let me just recall a definition here. So the question for us is which complexes are shelling completable. And again, we notice that if you ever kind of happen to become a matroid, then you could finish it. Okay. And so one more definition. A simplicial complex is vertex decomposable. Decomposable. Okay, just fit it. If either delta is a simplex or there exists a vertex in delta such that, well, let me just put it this way. So such that the deletion of V and the link of V are also vertex decomposable. So, yeah, I know this is a lot to take in if you haven't seen this before. So let me just not lie. So I want to assume that this thing is pure. You know, I want to just I want to write down this definition. This is a notion that I think Provin and Valera introduced, you know, some years ago in the context of, I think, kind of operations research and, you know, optimization questions. But let me just say that vertex decomposable complexes are shellable. And the last kind of result I'll mention, and then I'm out of time, I'm already out of time, is that, so this is a theorem that I prove with Suho O, is that if delta is vertex decomposable, then delta is Schelling completable. Okay. So again, this is these vertex decomposable complexes are a special class of shellable complexes. They include, I should have said, so they include the independence complex of matroids and also shifted complexes. They again kind of arise in nature. And what we could prove is that if you start shelling something, and if at any point you get to a vertex decomposable complex, then you can finish it off. Okay. Now, of course, Simon's conjecture says, you know, that, well, it's a stronger statement and it's still open, right? That says that I just need to be a shellable complex here. But we say that, well, if you ever happen to be vertex decomposable, you can do it. And the last thing I'll say just in words is that it turns out vertex decomposable and shellable are actually like two extremes of a family of classes of complexes that extrapolate between the two. And so that's kind of, you know, kind of future complexes, what other complexes, future research, what other complexes are Schelling complete. So I think I'll end there because I was told I'm already 3 minutes over. So thanks for listening. Happy to take questions.
Yeah, thank you, Anton. Are there any questions? So if you have, you can unmute and ask directly.
Hello. Hi. Hello.
Hello, Rajiv. Is that your name?
Hi. So you have given the extendable shellable condition, and
Yeah.
you have defined for the pure simplicial complex. Is it defined for the non-pure also?
That's a good question. Well, you got to be careful because, you know, as you might know, when you're not pure, you kind of insist that you shell the big pieces first, right?
Okay.
And so there might be a definition where you kind of build that into the extendable shelling, that like any shelling that does the big pieces first can be extended. You know, you can't make the same definition, but yeah, I imagine you could probably write something down. I haven't really thought about it, but it's a good question. You know, I think the extendably shellable complexes are already mysterious enough, so people haven't really.
Okay. And another thing, as shellability implies equivalent to some linear quotient of some ideal.
That's right.
And is there any algebraic condition for the extendable?
Okay, another good question. I mean, you could just say that it's, you know, it's equivalent to saying that if you have a linear quotient, if you have an ideal of linear quotients, then whenever you know, any sub-ideal that has linear quotients can be extended, right? It would be just the same.
Okay.
Right, because as you know, right, a linear quotient just means you have an ordering of the generator, so that every time you add a generator, this particular colon ideal is, you know, generated by a subset of the variables. And so, yeah, it would just be that whenever you have a sub-ideal that has linear quotients, you can extend it by adding generators that are also that have linear quotients.
Oh, okay.
I mean, and that's a good question that I was hoping somehow, you know, some algebraists had studied, but as far as I know, they haven't.
Okay. Thank you.
Sure.
Do we have any other question from anyone?
Can I ask just like who's here? Is it people who study? Is it students? Or I know there's some faculty here, but what is this group? This is the mostly topological combinatorics people, or just out of curiosity?
No, it's a combination of all community algebra and topological combinatorics.
Okay, so there's commutative algebra as well. Okay. Yeah, so hopefully everyone got something out of it. I mean, I don't know if there's any chordal graph theorists here, but has anyone thought about these higher dimensional chordality things? I don't know if that's come up in any of these talks or. Because I should say that's a big industry of this kind of, this higher dimensional chordality is actually a big topic right now, mostly inspired by this Froberg's theorem. So, okay, so if there are commutative algebraists in the room, that you probably already know this, but this notion of having a linear resolution over every field, right, over any k, it's kind of an open question that if you can characterize that for non-quadratic monomial ideals, can you characterize the property of having a linear resolution over any field in terms of some combinatorial property like you do here? And that's why a lot of people, they take this notion of chordality and they try to generalize it to higher dimensions. So this is just one way. It turns out to be equivalent to having linear quotients, which is, so it means it's not anything new. But anyway, this kind of interesting work that, not done by me, but check that out if you.
I think that Froberg result for the chordal graph, it is for all the powers have linear resolution.
That's also true. That's right. Yeah. All the powers have linear resolution. Yeah. And it's also, even for the chordal, it means that you have linear quotients, actually. So that's actually how I kind of got thinking about, right. So that's how I got thinking about this stuff, that, for the quadratic ideals, having linear quotients is the same as having linear resolution, which, as you said, is the same as having all powers having linear resolution. Yes. Yeah, so it's touching on some of that stuff.
So I have a question here. So when you talk about the edge ideal and all these ideals, you have the independence complex associated with the graph. And we know that the independence complex of chordal graphs are shellable sort of. Yeah, so there's always wedge of spheres or something. So the independence complex of some graphs in case of like whether extendably shellable or shellable completable. Whether this has been explored or something.
So the independence complex, I mean, so which graph are you talking about right now?
Maybe
these graphs?
Chordal graphs or
like, so the graph here? Yeah, so you're right that, I mean, the relevant kind of Stanley-Reisner complexes that I'm looking at are going to be the independence complex of these things. So, I mean, I guess maybe I didn't hear the question. What was the question?
So the question was independence complexes of like chordal graphs, are they sort of extendably shellable or shellable complete?
Oh, are they extendably shellable? They are definitely shellable. In fact, they're vertex decomposable.
Yes, they are vertex.
Okay, I see. So you're asking if they are extendably shellable. Well, I'm going to say no, right? Because yeah, I mean, because they can't be in general extendably shellable, right? I guess because so as you said, they're shellable, and they are flag complexes. I mean, they're the same as just flag complexes, right?
Yes.
So your question basically is, if you have a shellable flag complex, is it extendably shellable? And I actually don't know that, but it's got to be no, I guess, right? I mean, I'm guessing that these triangulations of spheres are going to be flag, and they're not, like the Ziegler example, it's a shellable complex that's not extendably shellable. And I don't know, but I'm guessing it's either flag or you can make it flag.
Mm-hmm.
Yeah, that's a good question. I bet there's an obvious answer that I don't have right now, but my guess would be no. But I see what you're saying. Oh, wait. Oh, no, wait, hang on. No. So sorry, the answer is yes, right? We proved that because that follows from this theorem, right? So those guys are actually vertex decomposable.
Mm-hmm.
So it actually is extendably shelled. So I take it back.
Yes.
So whenever you have it, so that's kind of the point of this theorem, that many complexes that are shellable and in fact turn out to be vertex decomposable, especially like in the combinatorial world, as you probably know. And so once you have a vertex decomposable complex, you can complete it to a shelling of the. Okay, but hang on, no, so they got to be a little bit careful because. Yeah, I take that back again. So two take backs, because this is saying that if you have a vertex decomposable, you can complete it to a shelling of the K skeleton, right? And extendably shellable, as you know, says that you can start with a subcomplex and then finish that off. So yeah, so I still don't know. Now I go back to my original answer. It must be no, because if you give me the independence complex of a chordal graph, I don't know that those initial, those subcomplexes are necessarily vertex decomposable. In fact, they're probably not, right? Does that make sense? So
yeah.
maybe I should think about it before I
So when
say
I think
more.
about it from the direction of flag complex, I can somehow.
So your question is, are independence complexes of chordal graphs extendably shellable? Because you're right that they are shellable. Okay, so I'm gonna just say I don't know. I think that's the best way the safest answer. But I like the question.
Not maybe just for the chordal graph. There are some characterization of the classes where, like odd hole free, if you say, they all have the simplicial vertex. So. So if you go through the proof of the independence complex of chordal graphs, the same proof works for odd hole free graphs, and they will always be scalable.
Well, let's see. So if you take a subcomplex of the independence complex of a chordal graph, is that also the independence complex of a chordal graph? Yeah. So what I'm thinking is, so let's say that your independence complex of the chordal graph is delta. So this is like end of G, right?
Mm-hmm.
And so now if I start with a shelling of delta, a partial shelling now, is this also the independence complex of a chordal graph? I mean, this is just a bunch of independent sets, right? So my question is this the independence complex of G prime, where G prime is chordal? Here, maybe we should take this offline. I like this question, but can we discuss later?
Yeah,
that's
sure.
Okay.
Yeah.
But actually, I don't know who's still here, but I was hoping to talk to maybe Anurag, Shuchita, and folks who work in this Hom complex stuff. I have a Hom complex question for people later, if you have a couple minutes.
So maybe if I can stop the streaming for the timing.
Yeah, I mean, unless there's other questions, is everyone happy? Well, everyone should think about this. I like this question. Again, I don't know if there's an obvious answer that I'm missing, but